Hi, welcome to Acid-Base Equilibrium. My name is Dr. English. Today we're going to be talking about working through a weak acid, strong base titration. Specifically, we're going to look at examining a strong base, strong acid titration curve, examining a weak acid, strong base titration curve, working through a weak acid, strong base titration, examining a weak base, strong acid titration curve, examining a weak diprotic acid strong base titration curve, and then finally talking a little bit about how to choose the correct indicator. Titration of a strong base by a strong acid. For titrations of a strong base with a strong acid, the hydroxide ions is in excess before the equivalence point, and the hydrogen ions is in excess after the equivalence point. So let's talk about a couple of the key features of this titration. Prior to the acid being added, the pH is high, typically around 13. As the strong acid is added, the pH only slightly decreases during neutralization, as we can see in this area right here. The pH changes very quickly near the equivalence point as the titration is complete. So here is our equivalence point. Equivalence, when you have a titration of a strong base by a strong acid, will occur at pH 7. The continued additions of strong acid is shown by the flattening of the bottom of the graph around a pH of 1. Now let's look at the titration of a weak acid by a strong base. When a weak acid is neutralized by a strong base, the graph varies in two distinct ways. The first thing is that the equivalence point is not at a pH of 7. A buffer region exists as you approach the endpoint. When doing calculations between weak acids and strong bases, re-examine the calculations done with buffers, as buffers will be created in this situation, and we'll be doing a lot more of this in a few minutes. Buffered solutions will result when the addition of the hydroxide ions to the solution, and we'll have a buffered solution until the buffer capacity is exceeded. Once the buffer capacity is exceeded, the pH will increase drastically. So our buffer region here is in this boxed out portion right here, and we're going to be talking about something known as half titration. And half titration, when we do refer to this later on, occurs right in the middle of the buffered region. The other thing that I want to point out about this is that when we look at this particular titration curve, because we're starting out with a weak acid, we're starting out at a pH that's not at 1 or less than 1. Our pH is higher. Also notice again, like stated before, the end point or the equivalence point is definitely above 7. And that is where your moles of hydrogen ions are going to equal your moles of hydroxide ions, and that is something to keep in mind, especially as we start doing some calculations with this. Consider the example of the titration of 25 milliliters of 0.1 molar HCHO2 methanoic acid with 0.1 molar NaOH, which we know is sodium hydroxide, and a strong base. So we have our chemical formula right here. And we're going to start out by calculating the initial pH before any base is added. So this is done as any weak acid using an ice table, calculating the value of X, which represents the hydrogen ion concentration. As in previous calculations, a Ka of the weak acid is needed along with an initial molarity of the weak acid. So in this case, our Ka is 1.8 times 10 to the negative 4. So the first thing that we're going to do is insert some of the values that we have into our ice table. So we know we're starting out with an initial molarity for HCHO2 as 0.1 molar. And that initially we do not have any hydrogen ions or its conjugate base in solution. Then ultimately we'd say to ourselves, okay, 0.1 minus X, we're going to have 0 plus X, 0 plus X, because ultimately what we're trying to do is find the hydrogen ion concentration, because if we can find the hydrogen ion concentration, we can calculate pH. So the next thing I'm going to do is set up my Ka expression. So Ka is going to equal my hydrogen ion concentration times my conjugate base, so CHO2 minus 1 all over HCHO2. And then I'm going to plug my values in. So the problem states that the Ka is 1.8 times 10 to the negative 4, and that's going to equal x times x. So I'm going to put x squared, and that Ka is pretty small, so I'm going to assume x is 0, and I'm going to put 0.1 on the bottom, and then I'm going to do the math to solve for x. And when I do that, I find out that my x, which I also know is equal to my hydrogen ion concentration, is going to equal 0.00424. Now that I have that, I can calculate the pH. So if I say pH is equal to the negative log of 0.00424, and I work out the math behind that, I find out that my pH is 2.37. And really, that's where I'm starting. So my pH is 2.37. Note that the resultant beginning pH will be higher than a typical pH value of a strong acid, as I just said. Now let's look at the pH after adding 5 milliliters of our strong base. So the first thing that we need to do is calculate the moles of the sodium hydroxide and the HCHO2. So to do this, I'm going to use the molarity formula. So molarity is equal to moles over liters. For the sodium hydroxide, I have 0.100 molar of NaOH. And they say, hey, the volume is 5 milliliters. So of course I'm going to change that into liters. So 0.005 liters all over 1 mole. And then I'm going to solve for moles. So when I do that, I'm going to have 0.0005 moles of sodium hydroxide. I'm going to do the exact same thing for my formic acid. But in this case, when I get to the volume part of it, I know that from what is stated at the very beginning of the problem, that I'm working with 25 milliliters. So instead of having 5 milliliters, my volume on the bottom is going to be 0.025 liters. And again, I'm solving for moles. And if I work that out, the number of moles that I'm starting with of my methanoic or formic acid, however you want to call it, is 0.0025 moles of HCHO2. So when titrating a weak acid with a strong base, the added sodium hydroxide converts the same amount of the acid also into its conjugate base. So at the very beginning, for the addition of the sodium hydroxide, I have 0 hydroxide ions. But here's my weak acid. I do have 0.0025 moles of my weak acid. I have water in here just because it's part of the equation, but really I'm not going to worry about that. And I also have 0 amounts of my conjugate base. Then what's going to happen is I'm going to add that 5 milliliters of sodium hydroxide. So when I do that, I'm going to say, all right, the addition of sodium hydroxide is 0.0005 moles. And if I add that, something has to neutralize it, and that's where my weak base comes in. So I'm going to say, well, if I've added that sodium hydroxide to neutralize it, I have to subtract out 0.0005 moles of that strong base. So as a result, at the end, after the addition, this will be neutralized. I will have 0.0002 moles of my weak acid left. But at the same time, if I've used up a little bit of my weak acid, I have made some of my conjugate base. So here's my conjugate base right here. So plus 0.0005 moles of conjugate base made. So after the addition, I will have 0.0005 moles of my conjugate base. So to summarize, the weak acid neutralizes the addition of the hydroxide ions that come in, but at the same time, my conjugate base, the CHO2 minus 1, is going to form as a result. Therefore, the concentration of this conjugate base is going to increase. After the addition of a strong base, The solution now contains amounts of both weak acid, weak base conjugate pairs. The solution is now a buffer. The Henderson-Hasselbalch equation and pKa can now be used to calculate the pH. So my initial Ka is 1.8 times 10 to the negative 4. I know that to find pKa, I'm going to take the negative log of my Ka. So if I say negative log of 1.8 times 10 to the negative 4, I can find that my pKa is 3.74. Once I have that, I can look at my Henderson-Hasselbalch equation. So pH is equal to pKa, I found that, plus the log of the concentration of the base over the concentration of the acid. Now I need to find these concentrations. I need to find these molarities. So I'm going to look at the molarity of my conjugate base first. Why not? So CHO2 minus 1. Looking back at my table that I just had, I know that I have made, as a result of this addition of the 5 milliliters of the strong base, I have produced 0.0005 moles of my conjugate base. And then I have to think about the total volume that was involved. So I added 5 milliliters, so that's 0.005 milliliters, plus my original volume, which was 0.025 liters. And if I do moles over liters, I find that the molarity of this concentration of my conjugate base is going to be 0.0167 molar. Now I'm going to do the same thing for my acid. So HCHO2. After the addition, I only have 0.002 moles of my acid remaining. And just like I wrote before, I'm going to say, well, I originally had 5 milliliters of my base and 25 milliliters of my acid. So if I'm going to add those together and then I work out the math behind this, I get from my concentration as 0.0667 molar. Now I can take those values and plug them in to the equation above. So pH is equal to pKa, which we said is 3.74 plus the log of the concentration of my base, which is 0.0167, all over the concentration of my weak acid, which is 0.0667. And if I work that out, my new pH is 3.14. So I can see that after the addition of my sodium hydroxide, my pH has gone up a little bit. Not a ton, but it's gone up a little bit, which is what the buffer is supposed to be doing. Now let's look at the pH after adding 12.5 milliliters of sodium hydroxide. So again, we're going to calculate the moles of sodium hydroxide when 12.5 milliliters has been added. So molarity is equal to moles over liters. We know that the initial molarity of the base is 0.1 molar, equal to our new volume here, which is 12.5. So we're going to convert that into liters. So that's going to be 0.0125 liters. And we're going to solve for moles. We're going to solve for moles. And when we do that, it's going to be 0.00125 moles of sodium hydroxide added. At this volume, 1/2 of the initial amount of HCHO2 is converted to the conjugate base, which we're going to see in a minute when we look at the calculations, resulting in equal amounts of weak acid and conjugate base. For any buffer in which the amounts of weak acid and conjugate base are equal, the pH will equal the pKa, and that's an important thing to notice. So let's see that as we go through. So before the addition, there's 0 amounts of OH. We have our initial amount of our weak acid, which is going to be 0.0025 moles. We're not going to worry about the water. And then we're going to have 0 amounts of our conjugate base. And then we're going to and then the addition is 0.00125 moles of our base, our strong base. So now our weak acid is going to neutralize that. So minus 0.00125. So as a result, we will have 0.00125 moles of acid remaining. But as we neutralize this strong base, of course, we're going to produce conjugate base. So we have an addition of 0.00125. And after the addition left over, we'll have 0.00125 moles of our conjugate base. And of course, the strong base that was added was neutralized. The key thing here to notice is that the moles of my weak acid and the moles of my weak base are the same. There's equal number of moles. And that is known as half titration. That is known as half titration, the half titration point. So now what we need to do is we need to figure out the pH at this particular point. So we're going to figure out the concentration of our weak acid and the concentration of our weak base. So we're going to have concentration of HCHO2 is equal to total number of moles, 0.00125 moles on top over our total volume. And our total volume is going to be 0.0125. That's the milliliters of sodium hydroxide that was added, plus the original amount of acid that we had, 0.025 liters. And if we work that out, we're going to get 0.033 molar. We're going to do the exact same thing to our conjugate base, so CHO2 minus 1. We're going to have 0.00125 moles on top, and then 0.0125 of the strong base added, and 0.025 like that, and that's our total volume of solution again, so 0.033 molar. And then we're going to put it into that Henderson-Hasselbalch equation. We can use the pKa that we calculated beforehand. So pH is equal to pKa. That was 3.74 plus log of our base over our acid. So our base is 0.033 molar for that concentration divided by 0.033 molar for that concentration. And you might be saying to yourself, oh, look at it, Dr. English. You know, the log of any number over itself is going to be 1, and the log of 1 is 0. And I'd say, hey, you're right. So this is the situation where pH is equal to pKa. So the pH here is 3.74. And we'll just say that again. pH is equal to pKa where you are at half titration. This is the situation where you have equal amounts of weak acid and its conjugate base. pH at the equivalence point. You can still calculate the volume of the base needed to reach the equivalence point using the formula VAMA is equal to VBMB. Weak acids require the same amount of base for neutralization as strong acids because they dissociate as they are neutralized. The volume at the equivalence point in acid-base titration does not depend on whether the acid is being titrated by a strong or weak base. It depends only on the amount, in moles, of acid present in solution before the titration begins and on the concentration of the added base. pH at the equivalence point. At the equivalence point, 0.00250 moles of hydroxide has been added, and therefore all the formic acid has been converted into its conjugate base, CHO2 minus 1. So initially, we will have 0 hydroxide. We will have our initial amount of our weak acid, so 0.00250 moles of our weak acid. We're not going to worry about the water, and there is 0 production of our conjugate base. At the equivalence point, we are adding 0.0025 moles of our base. As a result, that weak acid will neutralize it, so 0.0025, and we're going to subtract those from each other, and we get a big fat 0. Our strong base was neutralized, but at the same time, of course, we have now created 0.0025 moles of our conjugate base. So after the addition, we have 0.0025 moles of our conjugate base remaining. At this point, with all of our weak acid consumed, the solution is no longer a buffer, but only contains CHO2 minus 1 as the weak base. To calculate the pH, the moles of the conjugate base is divided by the total volume of the solution at the equivalence point to find the concentration of CHO2 minus 1. So we're going to take our moles of our conjugate base, 0.0025 moles of our conjugate base, and we're going to divide it by the total volume. So the initial volume of the acid, which is 0.025 liters, plus the amount of sodium hydroxide that was added, so 0.025 liters of that. And if we work that out, we will get a concentration of 0.05 molar CHO2 minus 1. And from that, we can go on to try to figure out the pH. Because remember, now we have this situation going on. So we have CHO2 minus 1, and it is in water. It's our conjugate base. So now we have a weak base. So this is our weak base. Now the water, that's also there, of course, is our weak acid. And as a result, we will produce a little bit of our conjugate acid, a little bit, so HCHO2, and also some hydroxide, OH minus 1. And we know that these amounts will be relatively low, but we need that. We need that because we are trying to figure out how much hydroxide ions are in solution, because if we can do that, we can find hydrogen, and then we can figure out the pH. So what we just looked at was the equilibrium reaction for the conjugate base in water. So initially, from the concentration of our conjugate base, we know that we're starting out with 0.05 molar of our CHO2 minus 1. And at the very beginning, we don't have any of our acid or any hydroxide ions produced. Then we're going to do 0.05 minus X. We're going to do plus X, and then we're going to take it to the next step. So the next step is to find the Kb using the initial Ka given, and then calculate the concentration of the hydroxide ions in the solution. So we know that Kw is equal to Ka times Kb. So if we rearrange this, Kb is going to equal Kw over Ka. So we're going to have 1 times 10 to the negative 14 all over 1.8 times 10 to the negative 4. That was our original Ka that we started with. So now we have a Kb that is equal to 5.55 times 10 to the negative 11. So we're going to write our equilibrium expression using our Kb. So Kb is equal to our weak acid, HCHO2, times our hydroxide ion concentration, all over our conjugate base, CHO2 minus 1. Plug in our values, so we know Kb is 5.55 times 10 to the negative 11. And then we're going to have x squared on the top, and that's a really small number. We're going to assume that x is negligible, so we're just going to put 0.05 on the bottom. And then we work this out, and we figure out that x, which we also know is our hydroxide ion concentration, is going to equal 1.7 times 10 to the negative 6. Now we can find pOH. So once the hydroxide ion concentration has been determined, the pH can be calculated. The concentration of the hydroxide ions is equal to 1.7 times 10 to the negative 6. So to find the hydrogen ion concentration, I'm going to have 1 times 10 to the negative 14, which I know is my Kw, 1.7 times 10 to the negative 6 on the bottom, which is my hydroxide ion concentration. So if I work out the math behind this, my hydrogen ion concentration turns out to be 5.88 times 10 to the negative 9. So once I have that, of course, I can do pH is equal to the negative log of my hydrogen ion concentration. So 5.88 times 10 to the negative 9. And therefore my pH turns out to be 8.23. We are definitely in the realm of basic solutions. So note that the pH at the equivalence point is not neutral, but basic. The titration of a weak acid by a strong base always has a basic equivalence point. This is why in titrations featuring a strong base of known concentration, added to a weak acid of unknown concentration, PHTH, otherwise known as phenolphthalein, is a good indicator to use. pH after adding 30 milliliters of sodium hydroxide. Above 25 milliliters, the solution is now a mix of strong base and a weak base. The strong base completely overwhelms the weak base, and we can calculate the pH by considering the strong base alone. Step 1. The hydroxide ion concentration can then be calculated by dividing the number of moles of hydroxide by the total volume. So initial plus added volume. So molarity is equal to moles over liters. The initial molarity of my base is 0.1 molar, and the amount of base that I have added is 0.030 liters. So again, I'm solving for moles of hydroxide ions that I have added. And if I do the math here, I have 0.0030 moles of hydroxide ions. Then I want to say to myself, okay, now the initial amount of acid that I started with, because these are all snapshots in time, so that would be 0.0025 moles of weak acid that we started with. So we're going to have 0.0005 moles of base remaining. I can find my hydroxide ion concentration at this point in time by saying, okay, I have 0.0005 moles of hydroxide ions, and my total volume here is my initial volume of my solution plus the volume of the base that I've added. So that, and then if I work that out, I have a concentration of 0.0091 molarity of my solution. The pH can then be calculated using kW to find the hydrogen ion concentration and then pH. So I know hydrogen ion concentration times hydroxide ion concentration is going to equal my kW. So my hydrogen ion concentration is going to equal 1 times 10 to the negative 14 over 0.0091 molar, because that's the molarity of my hydroxide ion. And if I work that out, it's 1.1 times 10 to the negative 12 molar. pH is equal to the negative log of my hydrogen ion concentration, so 1.1 times 10 to the negative 12 molar. And if I work this out, my pH, if 30 milliliters of strong base is added to my weak acid, the resulting pH would be 11.95. So that's a snapshot of the pH at that particular moment after adding 30 milliliters of sodium hydroxide. Weak base, strong acid titrations. When a sample of a weak base is titrated with a strong acid, the curve resembles an inverted weak acid strong base titration curve. Calculations for this type of graph would be similar to the calculations done for the weak acid strong base titration curve. Note that the pH at the equivalence point is less than 7. Also, the acid-base indicator must be chosen with a Ka near to the hydrogen ion concentration of the equivalence point. That is, the pKa of the indicator must match the pH of the equivalence point. And this is really, really important right here. So let's look at our curve. At the beginning, we start with a pH representative of a weak base. So it's not going to be around 13 or 14. It's going to be less than that. We have our buffer region in this area right here where we know that the weak base is buffering the strong acid. Midway through the buffer regions, we reach the half equivalence point somewhere around here. So that's half equivalence point. And at this point, pH will equal pKa. And again, when you're looking for an indicator to mark this region, the pKa of the indicator must match the pH of the equivalence point, and we'll talk about that later in class and how you could see that in a problem. The equivalence point here is going to be below pH 7. We know at this point the moles of our acid are going to equal the moles of our base. And at the end, we're going to have a pH representative of a strong acid. Weak diprotic acid, strong base titrations. When a weak diprotic acid, so for an example, something like H2C2O4 or carbonic acid, where we see that we have 2 hydrogens here and 2 hydrogens here, is titrated, there are 2 equivalence points. 2 equivalence points. The curve is not as distinct because of the various proton donors and proton acceptors in solution. So what we're looking for here is 2 bumps. A bump right here where we lose the first hydrogen, and a bump right here where there's the potential to lose a second hydrogen. We could see an example of 3 bumps in this type of titration curve if we were working with something like phosphoric acid. Choosing the correct indicator. There are 2 methods for determining the equivalence point of an acid-base titration. The first is using a pH meter to monitor changes in pH. The second is using an indicator to mark a color change. The purpose of an indicator is to observe when the endpoint of a titration is reached. Acid-base indicators are generally weak acids, and we're going to represent them as HIN, as IN stands for indicator. So HIN would represent an indicator that's a weak acid. The volume of titrant at which the equivalence point is visually detected is called the endpoint. The 2 criteria for choosing the correct indicator are, for the indicator endpoint, pH where the indicators change in color, to be close to the pH of the titration at the equivalence point. Color change should be clearly distinguishable. Indicators exhibit one color when a proton is attached to the molecule and a different color when the proton is absent. So for example, bromothymol blue. As a weak acid, the solution will be more of a yellow color. And as a weak base, as in IN-1, we're going to see a blue color. And in the middle, where we reach our equivalence point, we'll see a green color, as we know that yellow and blue make green. So what did you learn? We examined a strong base, strong acid titration curve. We examined a weak acid, strong base titration curve. We worked through a weak acid, strong base titration problem. We looked at a weak base, strong acid titration curve. We examined a weak diprotic acid, strong base titration curve. And at the very end, we looked at the criteria for choosing an indicator. Need more help? Feel free to contact me. Have a great day.